Welcome friends to our channel Chemistry is Awesome. In previous video, I had given one question regarding the NEET, so that is on the board. 20 gram of following gases expand reversibly and isothermally at 27 degrees Celsius from same initial to same final volumes. The maximum work will be obtained in the case of dash molecules. Their options are A. Oxygen, B. Methane, C. Nitrogen, and D. Carbon dioxide. Its answer is very simple. So that is methane. So how it is obtained? We know the formula for oxygen, O2, oxygen molecule, methane, CH4, nitrogen, N2, and carbon dioxide, CO2. Here what is given in the question? 20 gram of following gases means mass of all the gas, it is 20 gram, so that is fixed. And all other conditions are also fixed. All other conditions are also same. Then by which formula we can find out maximum work? Formula for maximum work, that is Wmax is equal to minus 2.303 nRT log to the base 10 of V2 upon V1. So that is the formula. If all other conditions are same, N, R, T, V2 and V1, we have to only find out here N, number of moles. And mass is given, that is fixed for all the gases. Then how number of moles are calculated? Number of moles can be calculated mass upon its molecular mass. Number of moles means value of N can be calculated mass divided by molecular mass, molar mass. If molar mass is smaller, then the value of N is larger. And when value of N is larger, then the work done which is obtained in the process, so that will be a maximum one. So therefore, in which molecule molecular mass is smaller? Here molecular mass of O2, so it is 32. For CH4, it is 16. For N2, so that is 28. And for CO2, it is 44. So smallest molecular mass is of methane, and therefore maximum work obtained in this process is in case of methane molecule. Means here, if all the conditions are same, then the work obtained is inversely proportional to the molecular mass of the substance. If molecular mass is smaller, then work obtained will be greater. So therefore its answer is B, so that is methane. Today we have to go towards next point in this topic, so that is internal energy. Internal energy. According to new convention, internal energy U is denoted by the symbol U. In previous period, we saw the two derivations. Which are two derivations? Derivation for simple work or PV work is equal to minus P ext delta V, and derivation for maximum work Wmax is equal to minus 2.303 nRT log to the base 10 of V2 upon V1, and another formula minus 2.303 nRT log to the base 10 of P1 upon P2. So these are the two formulas we derived in previous period. Now we have to see what is internal energy in today's period. We know that various types of energies are there, we saw in this topic. But what is the internal energy? Internal energy of a substance is the total amount of energy associated with the substance and this energy is stored in the substance. That stored energy in the substance is called as internal energy. You see here, it is given in the definition of internal energy. It is the total amount of energy, so that is associated with the system. It is present in the system, and this total amount of energy present in the substance or present in the system is that internal energy of each and every molecule present in that substance. Means this internal energy is again of two types. One is potential energy and another is kinetic energy. You see here, internal energy, so that is one is potential energy and another is kinetic energy. We saw the definitions of potential energy and kinetic energy. Potential energy means it is the energy associated with the body when it is present at rest position. And kinetic energy means the energy associated with the body or the substance when it is in motion. Again, potential energy and kinetic energy, in their types, potential energy is intramole energy and intermole energy. Kinetic energy is energy of translation, energy of vibrational, energy of rotational. So these are the subtypes, but we are not going to learn in detail regarding these types. But when a body is associated with certain types of energy which is present in it, so that energy, so it is called as internal energy, and mainly internal energy is of two types, potential energy and kinetic energy. When a particular substance goes from one state to another state, or goes from initial state to final state. Suppose this is the body, its state is A and it goes from state A to state B. The energy at state A, a particular substance has its internal energy, suppose U1, and at state B, its internal energy is U2. Then we can calculate the change in internal energy, so that is delta U in between these two states. So how it is to be calculated? The change in internal energy delta U is equal to energy at final state B U2 minus energy at initial state U1. So in this way, the change in internal energy can be calculated. Here, internal energy of the substance, how it changes, and energy is transferred from system to the surrounding, or we can say when energy is exchanged from system to the surrounding, then its internal energy changes. How internal energy of the particular substance increases and how internal energy of the particular substance decreases. Internal energy of a particular substance can be increased by two ways. What are these two ways? The internal energy of the system increases. What are the two ways by which the internal energy of the system or a particular substance increases? How? When we supply heat to a particular substance, its internal energy increases, and by doing work on that particular system from its surrounding, in both the cases, internal energy of a particular system or a substance increases. And how internal energy of that particular system decreases. Conversely, we can say that if heat is released by that particular system to the surrounding, then its internal energy decreases, as well as work is done by the system on the surrounding, its internal energy decreases. Means internal energy of a particular system or a particular substance can be increased or decreased by two ways. These are the important ways. How internal energy of the particular substance increases? By supplying heat and by doing work on the system by the surrounding. And how its internal energy decreases? By releasing heat from that system to the surrounding and by doing work of expansion by system to that surrounding. We know that this internal energy depends upon its state, initial state and final state. So therefore, this internal energy is a state function. So this internal energy, so that is the state function, and this change in internal energy can be explained by giving certain examples. How internal energy of the system can be explained? So by giving, we will consider the 4 examples. Suppose when 30 kilojoule of heat is absorbed by the system and 20 kilojoule of work is done on the system by the surrounding. What change will take place in internal energy? So see, what is my question? If 30 kilojoule of heat is absorbed by the system, 30 kilojoule of heat is absorbed, means absorbed heat increases internal energy, means suppose this Q is equal to plus 30 and work W, so that is plus 20, both in kilojoules. Then internal energy of that particular system increases by how much amount? So that is internal energy of the system increases by plus 30 plus 20 is equal to plus 50 kilojoule. So this is the increase in internal energy takes place. If you consider in second example, if 20 kilojoule of heat is released from system to the surrounding, released heat is given by minus sign, 30 kilojoule means internal energy decreases, and 20 kilojoule of work is done by the system on the surrounding, means work of expansion, and is shown by minus sign, minus 20 kilojoule, here also kilojoule. Then what is the change in internal energy of the system takes place? Both are minus, means this much amount of heat is released by the system, means it is given minus, and this much amount of heat is decreased on the system by doing the work on the surrounding, means minus 20, so that is minus 50 kilojoule of heat is decreased. We consider third example. If 30 kilojoule of heat is absorbed by the system, then Q is equal to plus 30 and 20 kilojoule of work is done by the system on the surrounding, so that is minus. You see here, delta U is equal to total change in internal energy of the system can be shown by plus 30 minus 20 is equal to plus 10 kilojoule. And we consider last example. If suppose 30 kilojoule of heat is released by system to the surrounding and 20 kilojoule of work is done on the system by the surrounding, so what will be internal energy change takes place? Heat release, it is shown by minus 30 kilojoule, and work done on the system is shown by plus 20 kilojoule. So therefore total internal energy change is shown by minus 30 plus 20, means it is minus 10 kilojoule. So in this way, by explaining all these examples, how the energy transfer and change in internal energy taking place to a particular system or substance can be explained in this manner. Then we will go towards the next point. So that is first law of thermodynamics and its mathematical equation. First law of thermodynamics. First law of thermodynamics. Mix and its mathematical equation. Mathematical equation, or it is also called as formulation of first law of thermodynamics. Its mathematical equation means formulation of first law of thermodynamics. It is also called as formulation. Formulation of first law. This first law of thermodynamics, it is also known as law of conservation of energy. So this law is also called as law of conservation. Law of conservation. Law of conservation of energy. In thermodynamics, 4 laws are famous. But in this topic, we have to see first law of thermodynamics, second law of thermodynamics, third law of thermodynamics, and one more law is there. So that is 0th law of thermodynamics. But we will see what is the first law of thermodynamics. This first law of thermodynamics is also called as law of conservation of energy. Means here, what is the statement of first law of thermodynamics? Total energy of system and surrounding remain constant when that system changes from initial state to final state. You see here what is given in the statement. Total energy of system and surrounding remain constant when the system changes from initial state to final state. So what is given in the statement? Total energy of system and surrounding remain constant when the system changes from initial state to final state. We saw initially the two terms, system and surrounding. System is the part of universe which is considered under thermodynamic study, and surrounding is also the part of universe other than system. And this system plus surrounding, it is called as universe. Means the total amount of energy of the system and surrounding remain constant when that particular system changes from initial state to final state. While converting from that particular system from a particular state to final state, from initial state to final state, what the energy change is taking place? If suppose in that particular system exothermic reaction is taking place, then there what happens? Heat is released from system to the surrounding. When heat is released, then system's internal energy decreases and surroundings internal energy increases, but total energy of system and surroundings that remain constant. So that is the meaning of this statement. Total energy of system and surrounding remain constant when the system changes from initial state to final state, or when the system changes from one state to another state. I have taken one example. When the particular system, in that system exothermic reaction is taking place. If suppose endothermic process is taking place, melting of ice example. During the melting of ice, 6.01 kilojoule of heat is absorbed, and that absorbed heat is taken from surrounding. Means system's internal energy increases, but surroundings internal energy decreases. So therefore, the total energy of system and surrounding remain constant. So that is the meaning of statement. And this first law of thermodynamics can be stated in various forms, or their various statements are given. So what are the other statements of first law of thermodynamics? Other statement is that total energy of the universe remain constant. See other statements. Total energy of the universe remain constant. Next statement also given like this: total energy of an isolated system remain constant. Total energy of an isolated system remain constant. Isolated system remain constant. And third statement is given, so that is the law of conservation of energy. Energy can neither created nor destroyed, but it can be converted from one form to another form of energy. So these are the three different statements of first law of thermodynamics, but meaning of all these three statements, so that is same. What is the meaning? Total energy of the universe always remain constant. Then total energy of an isolated system always remain constant. What is by isolated system? We saw that energy is neither allowed to enter nor leave the system to the surrounding. So that is called an isolated system. So whatever be the total energy, so that present in that isolated system, it remain constant. It doesn't changes. So that is the total energy of an isolated system remain constant. And energy can neither be created nor be destroyed, but it can be converted from one form to another form. We saw these conversions in detail in previous periods. So when one form of energy gets converted into another form, means what quantity of one energy, so that is converted into another form of energy, so that quantity of energy, so that remains same. Means energy is neither created nor destroyed, means total energy of the universe always remain constant. So that is the law of conservation of energy, or it is also known as first law of thermodynamics. How it is mathematically expressed, or how it is formulated, means what is the formula of first law of thermodynamics, or how mathematically it is expressed, the first law of thermodynamics. We know that how internal energy of the system increases or decreases. We saw in detail by considering 4 examples. But you keep in mind that internal energy of the system increases by supplying heat to the system and by doing work on the system by the surrounding. If you supply certain amount of heat to a particular system, it absorbs the heat and its internal energy increases. Or if work is done on the system by the surrounding, then internal energy of the system also increases. Means here the delta U, means change in internal energy of a system, is increased by supplying heat Q to the system and by doing work W on the system by the surrounding. So therefore delta U is equal to Q plus W. It is the mathematical equation for first law of thermodynamics. And for infinitesimal change, by small change in internal energy of the system, it is also formulated or denoted as du is equal to dq plus dw. So this is also a relation which is shown for the first law of thermodynamics. This is the relation for infinitesimal change taking place in a particular system. Then it is done by du is equal to dq plus dw, and change in internal energy of the system, delta U is equal to Q plus W. So this is the mathematical expression or formulation of first law of thermodynamics.